Okay, so in my last video, I repaired this spectrum analyzer here, this HP 8591A. And towards the end of it, I talked about adding a tracking generator, in particular, this tracking generator here. One of the things I did was I brought out the first LO signal out to the back of this unit, but I kind of left it there because I was having problems with this unit. So what I thought I'd do is make a video just about adding a tracking generator here, and in particular hacking this BG7TBL tracking generator to make it work with this one, because I actually bought the wrong tracking generator for this unit. So we'll see how we actually get that working. So the BG7TBL tracking generator, the 2017-1126 unit, comes in a pretty nice solid aluminium enclosure like this. On the front you have a power light. What that power light actually tells you is it tells you whether the local oscillator inside the tracking generator has locked or not. One of the ways you can get that light to go out is to switch from internal to external 10 megahertz source. And because I haven't put a 10 megahertz source in, you can see it becomes unlocked. And if I turn it back to its internal source, it locks. You have a small dial here, which is frequency adjust, and you have a second dial here, which is your level adjust. So this is your output power. What you've got on the back, a 10 megahertz output here, sorry, input or output. So you can put in 10 megahertz, the same 10 megahertz reference from your spectrum analyzer to essentially lock these two together to get better frequency accuracy. You put your LO in here, and then you have an on-off switch here and your 12 volt power. Okay, so when I actually attached the output from this tracking generator into my spectrum analyzer, one of the things I noticed was I couldn't see any additional signal. Well, I could every now and then, I saw a spike or so on, but what I would expect to see is something along the lines of when I attach the broadband noise source. I expect to see I think this is a minus 10 dB output signal level. So I expected to see a line at 10 dB across the full range of the frequency of the spectrum analyzer, but I didn't. So what's coming out this tracking generator is, you can see there's spikes appearing at random here, but what that's happening there is the tracking generator only generates signals at the frequency that this spectrum analyzer is listening to, and that's shifting as it scans and performs a scan. And so what I'm going to do, first of all, is set the center frequency of this unit to 1 gigahertz, and then set its span to 0 hertz. Now, what that does, let me just turn off my second trace as well. Blank. What that does when you set a 0 hertz span on a spectrum analyzer is you change it from looking at the spectrum of frequencies to a time domain. So actually the scan here is just looking at one frequency called the 1 gigahertz frequency. Now, if I reset this spectrum analyzer, you can see I actually am getting a tone out of my tracking generator. So if I search for this tone is appearing at 600 megahertz exactly. Now there's two things here about this. So if I get this unit to auto set itself and actually track down that peak, this peak is appearing exactly at 600 megahertz, or pretty close, and it has a height of 28.9 dB. So there's two issues here. I expected this tracking generator at full output to put out a minus 10 dB signal, and I expected it to coincide with the frequency of interest for this thing here. So this is at 600 megahertz, but the frequency I'm looking at here is a gigahertz. So there is a difference of 400 megahertz precisely. So if I reset this now, and we watch this spike here, and what I'm going to do is I'm going to shift the center frequency of this device. Right, so there's the 1 gigahertz. I'm going to tell this one to actually peak search, and I want it to track this. Let's see if I can get it to track. Right, it's tracking the peak right now. So we're at 606 megahertz, 1 gigahertz down here. The 606 is just a precision issue with the fact that this is scanning over a very large range. So if I get the center frequency and I scroll it down 100 megahertz at a time, you see a few things. First of all, can you see some additional products here? So these are additional mixing products coming out of the tracking generator. And as I lower it, I get a worse response and some more mixing products down here. But as soon as I get to 400 megahertz, 300 megahertz, 200 megahertz, 100 megahertz, you see this tone appear here. You see tones appear actually everywhere, you know, so there's one here at 300 megahertz. I'm at 100 megahertz. I'm seeing tones appearing up here. And actually this tone, this starts to dominate. And this, as I approach 0 hertz, that's what my center frequency is. I've got a tone at 400 megahertz and a tone at 2.12-ish megahertz, 2.12-ish gigahertz there. So what's happening, right? What's happening? Well, clearly what's happening here is this tracking generator is putting out a tone 400 megahertz lower than what I'd hoped for, than the operating frequency of this spectrum analyzer. And interestingly, when I set the center frequency to this here, I get 2.12 gigahertz, which is actually the IF of this 8591A, and it's also the low end of the LO. So what's happening here? Well, it's pretty clear when you look at the adverts for the tracking generators what's happened. I've bought a tracking generator that is expecting an LO to be 400 megahertz higher than it is. Okay, so if you're looking for one of these tracking generators online, you can find them, at least in the UK, on eBay. But how you find them is actually listed as compatible for MS610 and MS2601 systems. Those are Anritsu spectrum analyzers. But I have noticed that if you look at other sites, for example AliExpress, you can actually find tracking generators listed for HP units, and they look exactly the same. So, and if you read the specifications, the specifications are a little bit confusing, but they do indicate that they work with this particular unit, and that they're tracking generator in the range 50 kilohertz up to 1.8, and they accept an LO somewhere in the range of 1.5 to 6 gigahertz. Now that's quite a confusing range, because you'd expect this range here and this range here to match up. But what's happening here is this unit can actually be used for a range of spectrum analyzers, and depending on their variation on their LOs, you have to use it slightly differently, or you order it slightly differently. Now, to kind of dig into that, what do I mean is happening? Well, if you have a look at a block diagram for the Anritsu MS610, you'll notice that in their front RF section, their first local oscillator, the thing that they actually use to downconvert the frequency of interest, it has a range of 2.5 to 4.5 gigahertz. Okay, so that's 2 gigahertz of sweep, but the lowest frequency that the oscillator will go to is 2.5 gigahertz, and that will actually correspond to actually an input signal of interest of around about 0 hertz, is when the LO is at 2.5, and when the LO is at 4.5, that's when it's going to be at the 2 gigahertz range. But if you look instead at, say, the HP system, what they do is they actually sweep from 2.124 up to 3.92, so this is for a 1.8 gigahertz sweep. And so this will correspond to 0 hertz. So you can see there's actually, depending on which system you pick, Anritsu or HP, there's going to be a difference in the LO signals, which actually corresponds to exactly 400 megahertz. So 2.5214 versus 2.1214. And that's what we're seeing. That's the problem I'm seeing here. I've bought this tracking generator that's been set up for an LO coming out of an Anritsu system, so it expects the LOs to be 400 megahertz higher than they are, and I need to somehow change the tracking generator to actually respond to LOs in the range 2.1214. Now, how does that work? Well, a tracking generator, this is actually out of the block diagram for the tracking generator for an 8591A system, and the tracking generator is quite a simple system. Really, it's just a mixer, and what you do is you put in the LO from the spectrum analyzer that you have, and you mix it with an intermediate frequency, and this intermediate frequency that you're generating here should actually be the intermediate frequency of the device. So that means I should be injecting a 2.1214 gigahertz signal in here into this mixer for the HP systems. Taking a look inside the tracking generator, first what I did was I popped it open, and I noticed that it's quite nice. They've left the PCB bare, that's used for the front panel and the back panel, and that's to make a good contact with the aluminum case to get a good shield around this whole thing. But actually internally there's some shielding as well. So there was a large shield here over this main RF section here, and this section at the front here, which houses the PLL, it was actually covered by its own separate shield as well. So there was a little shield for the PLL section. Now let's have a look at this and actually see if we can figure out everything that's inside here. So what we have over here is the input. This is the LO input, and then it goes through what looks like a little pi filter here before entering into one of these MMICs, which is a little amplifier. And the LO comes in through here to this device here, which is the mixer, and then it leaves out through these two kind of unknown MMICs, passes through another bit of amplification here, and then it leaves out through this hard coax here to the front panel. So that's actually your output there. Now at the same time, what we have is this chip down here, which is an ADF 45, or what is it actually, ADF 4350, and that there is a little PLL, so that actually generates our frequency we're mixing in. It comes through a little pi filter again, then a variable voltage attenuator, some amplification before entering into this mixer as well. So I've tried to actually follow Dave from EEV Blog's approach and actually write a little bit of use DaveCAD and write out what's happening here. So what you'll notice is the LO input here comes in, and then we have this little pi pad attenuator that gives us -3 dB straight away on the input. And I think that's partially to kind of give a good input impedance towards this amplifier, but also to kind of provide some isolation from this LO input and everything else. Because one of the things we've got here, this mixer, is actually going to lead to some unwanted products, and those will actually head back this way. And the worst thing would be if these products out of this mixer actually made it back into the spectrum analyzer and started to affect our measurements. So I think part of the reason why we have an attenuator, then gain, then attenuator, then gain, then attenuation before the mixer is not only to boost this LO input up to the kind of strength needed to drive the mixer, but also to provide isolation. So that's what you can see here, the attenuator, gain, and attenuation. Now, all of these chips that you see like this, these 3-pin devices, are actually the same +20 dB SBB 5089Z amplifier. Now, if you look at that whole stage from the LO input up to the mixer, you get around about +31 dB there. So that should be plenty of power. I measured the LO coming out of my spectrum analyzer, and it's about -10 dB. So this +31 dB here should be more than enough to get it up to the requirements for this mixer here. Now the mixer itself, this device down here, is actually a H213 mixer, and you can see it's designed for down conversion, so it's expecting something in the range of 1.5 to 4.5 gigahertz in, and it supports up to about 1.5 gigahertz out, including DC. Now you'll notice that's actually a little bit below the specifications I saw for this unit. The unit was spec'd, the tracking generator was spec'd to up to 1.8 gigahertz, and yet this mixer says 1.5 gigahertz, but it probably just starts to tail off at that point. There's some interesting things here though. So what we notice is there's another kind of stage of gain here, and a little bit of attenuation either side of this device here, but this device here is actually a voltage controlled attenuator. So it can actually provide up to 40 dB of loss here, and I think that's part of some kind of automatic level control circuit. So if you have a look, we have these two stages of F1 and F2, and I think these are output filters. I think they're there to filter out, say, the IF frequency coming through here and any of the unwanted mixing products that go above 1.8 gigahertz. So I reckon that's what that's there for. And then we have a little bit of amplification, but then we have this kind of collection of resistors and capacitors down here that I can't quite figure out. But what I think it is it's a sampling setup. I think this little, well, maybe you can't quite see it on the camera there. I think that this here might be a diode, and this is some kind of detector circuit here. So we've got a rectifying diode, a capacitor here that charges up, and then the voltage that you charge that capacitor to is actually read by this op amp here. So I think it's buffered by this op amp and read. And then that comes back out. The output of that op amp goes into the voltage controlled attenuator. So I think this is the level control. And part of what's being fed into it is actually this pot here. So you'll notice there's a little pot here on the board, but there's also this pot, this cable here that goes to the front panel pots. And that's the level control pot. Now, it's a bit strange to see. You'd think seeing a pot on the board like this and seeing a socket here as well, that this somehow was a trim pot and then the actual, the front panel pot was here. But actually, I think this board was originally designed to be used without this case, because this pot here does nothing when the front panel pot's attached. The front panel pot has a much lower resistance than this one, so it kind of overrides its whatever voltage it's trying to set. So I think you can disconnect these front panel pots and actually use the board without them being attached. So that's all they're there for. Okay, what else do we have? Right, over in this corner up here, this is the 10 megahertz reference. And that's, as you have your switch here on the back, which is selecting between this internal reference and the external reference. And then they have a couple of these chips down here. This chip here in this corner, this is, I think, a voltage level translator, and I think they're using it to kind of buffer this potential external or clock, or actually buffer the internal clock before it goes out. I think that's what that's for. We have this little connector here. That's actually for the 10 megahertz reference in. That's easy to see. And then we get down to the actual PLL, and the PLL here is this ADF4350, and you see this a lot in devices, or the ADF4351. You see these devices in all of these cheap spectrum analyzers, especially the ones produced by BG7TBL, but also other groups as well. Now this PLL here can output between 1.375 megahertz all the way up to 4.4 gigahertz, depending on how it's configured. And it's controlled by an SPI bus. And that SPI bus, you can see just here, just before it starts to pass under the shield. So you see these 4 vias are actually what takes this SPI bus out from this and underneath the shield, and then it reappears immediately afterwards. And what you actually see in this bottom corner here are the traces going to an 80 Mega 8A. So that's a Atmel microcontroller. That actually seems to, it only has 2 jobs really. It seems to actually program this 84530 and set the frequency that comes out of here, and it also seems to control the front light, so it flashes that light depending on whether you've got lock, and that's what this LED here is. Now what you might notice is there's a lot of this, there's this extra cable that's kind of in our way. What that is, I could have unplugged it, that would have made sense. That actually is my knockoff WaveShare XP11 AVR ISP programming header. And essentially these pins here I actually added myself, so that this wasn't populated before, but this is clearly a programming header for these chips, for these system programmers. Now, it wasn't populated, which was kind of surprising to me, because they must have programmed this somehow, and I kind of assumed that they just must have used pogo pins or some other kind of temporary connection to program this. However, interestingly, they actually have a 4-pin header here, one either side of its ground, but the middle 2 pins are actually marked here, RX and TX. And if you have a look, they seem to be attached to the serial pins of the 80 Mega. Which is kind of interesting, because they're not used. There's no serial input or output on this thing. Although there is kind of a blank hole here. I'm not sure what that might be for, but perhaps for a serial connector there, yeah? So maybe one of those, headphone jacks repurposed into a serial port, RS232 serial port. And they have the same chip down here, which is over here attached to the clock, and I think that's that level translator. I think that's a level translator for the RS232 bus. Now, it's interesting that that's populated and this one isn't, because that makes me think that actually this 80 Mega 8A hasn't been programmed using an ISP, or it was programmed once, but somebody put a bootloader onto it and then actually used the serial port here to program it further. So I think this is probably set up as an Arduino, which is pretty cool. So certainly what I'm going to have to do to make this whole thing work is I'm going to have to reprogram this PLL to actually output the correct frequency that I need. So basically change it by 400 megahertz, lower its output frequency by 400 megahertz. And I'm going to do that by reprogram this 18 mega A here using an Arduino library. And yeah, and then actually there's some options here to maybe add serial output here and actually do something else with this. Maybe make it so that I can change the offset to allow kind of offset sweeps and so on. That would be very cool. Okay, so there is one other thing that I've already done. You can see these red wires here. What I've actually done is soldered on a series I've soldered on some wires onto the pins of the 80 mega A that actually correspond to the bus, the SPI bus of this ADF 4530 here. Sorry, 4350 here. And what my plan is, I'm going to look at what commands are actually sent to set up this, just to make sure that I have an idea of how this is configured as it stands. Because I probably want to just tweak the configuration. I don't want to, start exploring about the full setup of this. So I've put 3 pins in to measure that. And you'll notice there's a 4th pin here, and that's actually, there's a separate PLL lock line. So this actually has it has a chip select, it has an SPI data in, it has a clock line for the SPI bus, and then it also has a PLL lock line that informs when this actually has locked to the 10 megahertz reference and it's outputting its signal. Now that line is just either high or low, and yet you'll notice the front panel LED actually is on solid continuous when it's locked and it's blinking when it's not. So clearly the 80 mega takes this PLL lock in and then programs this output light. And I think what you'll see is when we look at the data lines, I'm going to go now, we're going to use my DS Logic Plus here to actually sniff these data lines. What you're going to notice is this PLL lock line is also used by the 80 mega A to figure out when it should stop reconfiguring the PLL. So let's see that. So, the only things I haven't looked at here is the frequency adjust. I haven't really figured out exactly how that frequency adjust works here. Probably some kind of tuning up here in this area here. And this part here is pretty straightforward. You can tell by the inductors that you've got some kind of switch mode power supply here. Certainly this thing here is a 3.3 volt regulator for the actual microcontroller. And interestingly, this is the external crystal, so they are using an external crystal for this, and to run this 80 mega. And let me just check. It's an 11.0. Okay, I can't see at this angle. 11.0592, I think, megahertz external crystal, which is an odd, frequency you might think, instead of like 10 megahertz or 8 megahertz or whatever. But that frequency is perfect for running external RS-232 buses. So it allows you to get precise, baud rates for a RS-232 bus if you divide it down correctly. So clearly, this is again lending weight to this being an RS-232 bus just here. Okay, so let's take a look at the logic analyzer. Let's look at what's going on with the communication here and see if we can figure out what frequency it's set to, how it's set, and so on. So I thought I'd show you how I set up PulseView and generally how I use it to debug things like this. So the first thing I need to do is connect the DreamSource logic analyzer. So this is what I'm using. I'm using a DS Logic. Now I really like the logic analyzer, but they've got a bit of a bad reputation with PulseView. They kind of ripped it off a little bit and made their own software called DSView, and the PulseView developers aren't particularly happy about that. And it has to be said, the DSView software has fallen by the wayside. I can't do what I'm going to do today with it, for example. So I feel a little bit bad having bought this unit and not supported PulseView, but I'm going to give back to him by developing some device plugins. So karma will balance in the end. Anyway, the first thing I'm going to do is set this to a reasonably high sample rate. 50 megahertz should be more than enough to capture anything on this SPI bus. And what I'll do is I'll tweak that later on. For performance reasons more than anything, lower it, but for now I want to make sure I don't miss anything. I'm going to do 50 megasamples to capture one lot of data, and I know I'm only using the first 4 channels, so I'll just enable them. So what I'm going to do is start a run of logic analysis and turn the device on at the same time. So I hit run and then turn the device on. And there you go, I can see something here. So what I can see here is what we'd expect on the SPI bus. I'm seeing something like a clock line here, so I'm going to quickly rename this. We'll call that clock. This is going high and low in between the clocks, so this is clearly some kind of chip select, so that's what I'm going to call that. And then this here appears to be your actual data line, so I'm going to call that, I can never remember whether it's MOSI or what, serial in, serial out, whatever. This final one pin here is the, the lock, the PLL lock line, so that's what we'll put that there. Now, the really nice thing about PulseView, pretty much the best thing about PulseView is the fact that it has these decoders. So for example, I can come here and add an SPI decoder. Now, straight away actually, because I wrote clock, MOSI, and chip select, it seems to have configured this immediately. So that's really quite nice there. Now you can see what it's done is it's decoded the bits, and it's also arranged those as 8-bit words here, so it's given me 2 lots of hex codes there to tell you what that is. Now that's nice, but it's not as nice as maybe seeing the packet that's being generated, and you can do that by stacking decoders. So fortunately, this PLL that we have in this device already has a decoder in there, an ADF435X. So this is for the O or the 1 version. And there you go. I mean, come on, that's very impressive. I have now decoded packets where it's decided what it's seeing here. Now the way that this ADF is programmed, ADF435O is programmed, is you have 5 separate registers, and the last 3 bits of this select which register you're writing to, and then the contents of the register appear. Now, some of these registers don't use a lot of their actual contents. You'll notice this is really just blank, this thing here. Register 5 just has this, pin mode, digital lock detect, set enabling that, or whatever. Register 4 has a little bit more interesting stuff. So we've got, what kind of divider do you select, and so on, like this. You can see like what kind of powers are you going to select, and so on. So that's in register 4. Register 3 again has more clock dividers. It's quite a complicated formula to calculate the output of this, and you have to make some choices about how you implement each frequency, depending on what you want, whether you want kind of accurate frequency, or whether you're and you want to accept increased phase noise, or you want low phase noise and inaccurate frequency. Okay, and then here's some more setups here around charge pump and so on. Okay, so register 2, register 1, register 0. So it's quite clear that what we're seeing here is we send out 5, 4, 3, 2, 1. So we're a bit of a break between 3 and 2 for some reason. Register 1 and register 0. Sorry, there's 6 registers, not 5. But then what you'll notice is as soon as we get to register 0 here, what happens is we then send out register 4 again. And then afterwards, you'll notice this is a completely blank. Yeah, you see there's no activity on the data line. A completely blank register 0. I don't know why the decoder's not been able to decode that. Maybe there's something unexpected here. But these 3 bits here select the packet. So what they did was they've sent out a register 4 followed by a register 0. And that's everything we've managed to capture. Now, one of the things you notice is this PLL lock line hasn't gone through a transition, so I kind of want to see what happens when this thing locks. So what I'm going to do is quickly zoom in and just see how many data points I got here. Okay, I got a lot of data points here. So I think if I turn on measures and I move this to here, we can measure the width of the clock. So the clock itself is running at about 250 kilohertz. Which is very slow. So if I want to actually get a good measurement of this clock, 1 megahertz is more than enough. And instead of doing 1 megasamples, I'm going to do 2 megasamples. That'll be more than enough. So the reason why I'm lowering this is the performance of PulseView. It's running just fine right now, but the performance of the decoders and everything else depends quite a lot on how many points you have to process. And it has to be said, these decoders are all written in Python, which isn't the most performant of programming languages. So it just helps a little to reduce the sample count. Right. The other thing I'm going to do is I'm going to actually trigger. So I've changed the trigger to be on the clock line. So you can see nothing really happens when I first switch this thing on. All the lines are low, and then you start to get transitions immediately on the clock. I was kind of surprised. I thought you'd see the chip select kind of go high at least to allow the ADF to reset before it then goes low and then goes high again. Because obviously chip select is low when you're writing to it, but it seems that the 80 mega just jumps straight into it. But you know, the system seems to work just fine. So right now with this transition setting, I'm going to get this right at the start, and I'm going to see what happens when the PLL lock comes in. So let's hit run. I'm going to turn off the unit. I'm going to hit run. Now it's not triggering until I turn on the unit. It triggers. We get 2 seconds of data, and there you go. Now, what you'll see is right at the start of this capture, those same packets that we saw earlier. Oh, something odd happened there. That first register, register 5, wasn't received, or isn't decoded. That's interesting. You see, this is kind of part of the problem I have with the way that this thing is, the way that this 80 mega isn't actually using the chip select first, allowing time for the, you know, well, and it also looks like they've put out too many clocks. Something very odd there. And the decoder's struggling to decode things. It looks like I'm getting too many clocks. What is going on here? Let's try a slightly higher sample rate and try running that again. See if I've just got a noisy, I've probed this in a noisy way. Let's go and have a look at this. Okay, that's decoding a lot better now. I think maybe I needed more higher sample rate perhaps. I mean, yeah, okay, a higher sample rate was needed. Okay, great. So yeah, I'm seeing register 5, 4, 3, 2, 1. But now what you'll notice is because I increased the number of samples and lowered the sample rate, I can see in this single capture here a second event. So what we notice here is that the PLL lock there's where actually the PLL reports that it's locked. But what precedes that is actually another packet, 2 packets from the 80 mega. So it's sending out another register 4 and, would you believe it, another register 0, although the decoder's again flaked out here. So it seems to be sending 4 and 0 on repeats, because that's what happened. Oh, I've zoomed out way too much. That's what happened over here. You notice we actually sent out register 5, 4, 3, 2, 1, 0, and then we sent out register 4 and 0 again. So what I think the 80 megas programmed to do is configure the first all bytes and then repeatedly send out register 4 and 0. But you'll notice it doesn't send anything out as part of this register 0. So maybe this is part of how you operate this ADF. You have to configure all registers and then allow some setup time perhaps. And then once it's kind of settled, you know, and here we can see clearly that the setup time is something on the length of 720 milliseconds. So it's giving it a good while before it then actually sends through register 4 and register 0 again, and that seems to then cause the ADF to actually lock. So what I'm going to do is I'm going to now save this, and I can now use this as the basis of what I'm going to implement. So I'll probably do the same thing. I'll introduce a 700 millisecond wait between this. I'll get it to repeatedly output this every time this lock goes low. So every time it loses lock, I'm going to get it to send this. And I'll get it to send exactly the same packets and see if we can just essentially get it working the way it was, but with my own Arduino code. And then what we'll do is we'll dive into this band, clock divider and so on, clock divider modes, and see if we can configure it for the right frequency for the HP units. Okay, so let's talk about setting up programming this 80 mega 8A. So what I had to do was first of all add additional board manager URLs, and I've added this mcdude minicore board manager URL. And then once you go to your boards manager, you can actually, well, okay, this takes a little while, so I'm going to try and cancel it. Yep, if I type minicore, you'll find that in here now, and you can install. I'm currently using 2.0.2, so that's installed. once that's installed, I'm actually using 2.0.3 there actually. You can then come along to boards, scroll down, and for me right at the bottom I have this 80 Mega 8. Then if I want to click clock, you'll notice I have a certain number of selections. So I have 60 megahertz external, 20 megahertz, and so on. But if you remember from the teardown, this board actually has an external clock, and it has a peculiar a frequency which is actually very good for serial communication. So what I would do then is we want to modify this system, this setup here, so that we can actually add that as a clock option. So to do that, you have to go into your Arduino data, packages, mini core, hardware, AVR 203, and what you'll find is there's a boards.txt file in there, and this is from the mini core setup. And what it tells you is it tells you a variety of clock rates and the corresponding board rates that you can use, and what they actually correspond to. That table corresponds to the pre-compiled bootloaders that are actually stored in this. So if you go into bootloaders, OptiBoot Flash, bootloaders, 80 Mega 8, and then look for the clock number that you're interested in. For us, the clock number we're interested in is this 11.0592 megahertz. If you look at 11.0592, there's actually a hex file for a bootloader which supports a range of UART speed. So this is the speed that you actually want to program the Arduino at, and it'll be the operating default speed of that UART. Well, actually, I think it'll probably be the permanent speed of that UART. So we're probably going to pick 11.5200 speed here, and you can see here it's supported, it's available there, but it's not currently in. This threw me a bit, but it's not currently in this clock selection here. And so what you have to do is you have to add it yourself. So to do that, we go back to boards and we scroll down to the end. Because it's at the end, the 80 Mega 8As here, there's a load of 8s, this is the general stuff, and then here in the menu, bootloaders, here we are, clock, this is what we want. So they have a 1 megahertz internal here, so what I'm going to do is just not duplicate that one, actually, because it's an internal clock. I want to duplicate an external clock one, so we'll grab that, and we'll put it at the end, because it's my Arduino, I don't care about having it in the correct position. And what's the speed? The speed was 11.0592, so we'll use that. This is where I wish I had Emacs installed. Okay, and the reason why I copied an external one is because you'll notice that there's these clock select bits and these clock option bits, and they have to be. If you look, all of the internal clocks have the clock option bit 1 set, and all the external ones have it unset. And then you actually have this clock select bits here, which is entirely for setting the speed of the internal oscillator. So you'll notice this differs to this. But when it's external, it seems that you set them all to 1. So that's what we want to do as well. The only thing we need to fix are the upload speed and the actual clock speed here. So this is just an integer compile time. 1, 2, 3, 1, 2, 3. So I'll just check that that looks sensible by comparing it against, say, that 80 megahertz one here. Just scooch it in. Yeah, okay, that looks like 11 megahertz. Okay, so pretty happy with that. I'm just going to check. They use underscores here instead of dots because it looks like dots the separator for the menu item. So I'll do that as well. The upload speed. Okay, we want to pick a bootloader that has corresponding upload speed, so I quite like this one. I mean, we can use a higher one. I don't know why I prefer that board, right? But I don't know, call it a quirk. I prefer using that one. And I think we're good to go. So that's our additional entry. So let's save that. Let's hop into Arduino. And I need to reload this. So we'll close Arduino again. Reload it. And now I'm hoping that I have this new clock speed. Awesome, great. So I've got the 80 mega, 11.0592, brownout detection enabled, bootloader on. Okay, so I actually had to stop that there because I went down a bit of a rabbit hole, and my theory that BG7TBL actually programmed this system via serial or via bootloader was completely blown out the water, because in order for the bootloaders to work, you actually have to have an extra pin. So you don't need just an RX, a TX, and a ground pin between the Arduino and your serial line, but you need I think it's the DTS pin, or you need a button or something you can short out on the board to actually switch the ATmega 8A into upload mode rather than just communicating across the serial. So what I did was I went back. I still needed to edit the mini core to support my external clock of 11.0592 megahertz, but I disabled the bootloader because I'm not going to actually upload over the UART. This COM port's now irrelevant because we don't use it to program. Instead, we use the in-circuit programmer that I have, and we go to upload using programmer. So that's how I actually program it. So what I did was I spent a little bit of time debugging, figuring out all the pins. These are the pins that everything's connected to, or at least the Arduino pins as assigned by the mini core setup. And yeah, here's the whole thing. So what I thought I'd do at first is just rebuild the original performance, just to check I got everything right. So I designate in the setup, I designate the pins I need as output and the PLL lock as an input. So all the SPI and the LED are all outputs. I then set them to a well-known state to start with. I want the clock to be low because it clocks up, it clocks high whenever I want to send something out. I want chip select to be high so that the ADF 4350 isn't it doesn't think something's about to talk to it when the system just turns on. And then what I did was I just write out the same bits that the BG7TBL did. So this is register 5, and what you'll see here is I've actually numbered the bits. These are the bits that are actually sent out. And I've also tried to understand what it was that the BG7TBL original firmware was doing. So you can see here Reg 5 just has one thing up here. It's just got 2 bits, AA, and they're set to 0, 1 actually in the packet that was sent out. And you'll notice these 3 bits at the end, just the number of the register that's being sent out. So 101 in binary is a number 5. So AA, it's the lock detect pin, and 0, 1 means that it's enabled. So what this means is we want to have the ADF 4350 output on its pin the status of his lock. So that's what we're pulling in via this PLL lock pen here. And then you just go on. So for example, register 4 here, there's a few bits of information set here. We want feedback to be the fundamental rather than after divider. We set a divider here, and so on. There was a couple of things that were quite unusual. First of all, the auxiliary output is enabled as well as the main output. So this ADF 4350 can actually output two RF signals, and both are enabled in this. So I'll have to check what's going on there because I'm wondering if they're combined, because that's something you can do. They seem to be in phase and seem to have the same frequency, because you can insert a divider between these two if you want to output like a harmonic of this or a divided frequency out of versus the main RF signal. Anyway, so how do I actually run the SPI? Well, here's a little bit of a hack. So the SPI library in Minicore actually only works on a set of pins that were not used here. So this again puts another nail in the coffin for thinking that this was an Arduino system originally, because yeah, they didn't use a hardware SPI. I think they did. And what you're going to see is basically I use the shift out to actually clock out on this line here these bytes that you can see here, these 2 hexadecimal characters, and doing this in software like this allows you to use any pin you like, but it's quite a lot slower than using one of the peripherals. And my communication speed is much slower than the original firmware. It doesn't matter because you only need to send this out once to the ADF on startup. But it does clearly show that BG7TBL was using some kind of peripheral and probably using the ATmega, the Atmel Studio to program this rather than Arduino. Because Arduino, you'd use the SPI pins. You'd make sure that your pin layout worked that way. I mean, he could have altered the core to change the pin, but I don't know, it just seems like a lot of effort. Okay, anyway, so here's register 3. Again, more things. Register 2, register 1, and then register 0. And then we get this repeat of register 4, register 0. And I think I figured out why they sent out register 0. In register 4, there's a couple of items here that are actually double buffered. So when you send the change out for them for register 4, they are not actually applied until a register 0 is sent out. So it seems that this register 4 here sets out a load of values, and then he clocks out a blank register 0, which actually is using invalid values for things like this integer value here. So it's not allowed this value of 0. But I think he's doing that just to kind of register this or force this reg 4 to actually sync. And then we get down to here, and again we send out a register 4, and we send out a proper register 0. I kind of don't, I still don't understand why he did that. I think you can just clock out all 5 registers at once, one after the other. You don't have to repeat or anything like this. So I'm probably going to get rid of that in my firmware. But I just wanted to see if I could get what he did working. So if we now pull out the PulseView and get a new session, what I'm going to do is turn off the unit, and then we are going to hit record at the same time. So after 500 milliseconds, we're seeing our packets go out. If you have a look here, we see the chip select go high very momentarily. So that's register 5, 4, 3, 2, 1, and register 0. And then what you notice is before register 4 clocked out, the PLL locks again. So I think because we're communicating so much slower than the original firmware, you can see that the ADF actually has time to lock, given that first 5 registers that were a valid configuration are put out. Now, that next, reg 4 and reg 0 actually isn't a valid configuration. That reg 0 there is improperly set up. This is a wrong integer value here. And you can see what happens is once that clocks out, lock is lost again. So that kind of just says, what the original firmware did was a bit strange. But then what you notice is the CS pin goes low again without there being any comms, and then the Mosey line goes high. And it's kind of a bit of an odd thing to see here, but what I think is happening is there's a small brownout at 800 milliseconds, and that's causing the ATmega to reset. So if we come along here, you actually see the original 5 packets again, along with a repeat of number 4 and number 0. So there's a small brownout happening at 800 milliseconds, causing the system to reset. But then we get to the end here, and we get these final 2 packets, the 4 and the 0 again, which then cause the PLL to lock. Okay, and if I just check, yes, we are actually seeing a peak 400 megahertz lower, so everything seems to be working. Right, so what I'm going to do is I'm going to try quickly moving these packets right to the start and just replace these. I won't bother doing all this kind of reset and wait. We'll just do it all at once and see if that causes the PLL to lock straight away. So let's give that a go. Okay, as an experiment, I just kind of made the Arduino code output register 5, 4, 3, 2, 1, 0, all with the kind of last values that were put out. And sure enough, if you look at SIGROC, what happens is those 5 values are put out, and you get a PLL lock almost straight away. We then see this brownout happen over here. The brownout doesn't seem to be enough to actually reset the PLL. It causes a little glitch here. We lose PLL lock for a very short amount of time, but then it seems okay. And I reset the system. After the delay, the ATmega actually restarts again, putting out its values, and sure enough, you get a small glitch there in the PLL lock, but that's it. So we have a pretty nice, pretty boring script here. About the only thing that I do is while I'm waiting for everything to stabilize, I blink the LED about 10 times, and once everything's kind of stabilized, I output all of the registers, and then essentially just while we don't have a PLL lock, I blink the LED slowly. I blink it every 700 milliseconds. Now what I need to do is I need to find a new set of values for all of these registers that works for my system, basically lowers the frequency that's coming out of this. And I spent a long time making a pretty nice spreadsheet that basically checked everything was in range and calculated the final RF. And then I went digging and found that there was actually a piece of software to help you control these chips. And you essentially pick the chip that you're interested in and then start dialing in the information that you want. Which was kind of annoying. I lost a bit of time on that. Anyway, so here it is. Here's the final script. This is the configuration I went with here. So we're targeting 2.1214 gigahertz as an output. I put this channel spacing on this script to as small as possible because essentially that just makes as narrow frequency as you can. There's my reference frequency, 10 megahertz. I've got this R counter. So this R counter here divides down the reference frequency. I've tried to make this R counter as small as possible. So 1 is the smallest value. The reason being, these clocks of this reference frequency are actually the points at which this phase detector here actually synchronizes. So if you want the lowest noise you can coming out of the system, lowest phase noise you can, then you want to have these synchronizations as often as possible. I could divide. There's an option here to double or halve the reference as well. If you double the reference, essentially the what do they call it? Clock rises and clock drops of the reference frequency. Each one is used as an actual edge to perform this phase detection. However, if you put this doubler on, you're relying on this reference frequency actually having an exact 50% duty cycle, and I'm not really sure that any of my sources have that. I haven't checked that. So I'm not using the reference doubler. If I can, I'm going to avoid that. If you divide the reference in half, you can actually guarantee that what's coming into this phase detector actually has a 50% duty cycle, and that's useful if you're going to use some of these fast lock modes that this thing supports. But then you synchronize, half as often. So I'm keen not to either double or half because I don't care about fast lock. I only care that it locks eventually, and I mainly care about phase noise. This prescaler here depends on whether you're trying to access high frequencies or low frequencies, and we actually at this point generate a high frequency signal and then halve it to get the frequency of interest. So we'll leave it in the 8.9 configuration. Feedback signal, this is what's coming back to actually go back into this phase detector to actually lock to our reference frequency, this our output frequency. Fundamental works fine for us here. Basically, if this didn't work, you might have to change your divisors to make parts of the circuit work. And it's because this prescaler supports a certain amount of frequency and then everything else supports another amount of frequency, a lower amount of frequency. So you have to play around with that if you're targeting higher frequencies. Over here we've got this in low noise mode. I've done experiments with low noise mode and low spoil mode. I can't see the difference for my application. DVDD, this is just what BG7TBL is using. I'm wondering if he's using this as to power something or part of his filter, so I'm not going to play around with that. Double buffering's disabled, don't really need it. We're not really changing frequency, so it doesn't really matter what that is. Charge pump current, I'm not sure what that should be set to, but that's what BG7TBL had it before, 2.5 milliamps. I'm a bit worried that somehow there's a filter as part of this feedback loop for this voltage control oscillator onto the reference frequency. I'm wondering if that somehow plays into that, so I'm just leaving it as it is. This just decides whether you want to have something that's fractional, so we have a fractional component here to our sigma delta converter that's actually driving our voltage control oscillator. We need it to be in fractional mode because you can see we have 7/25 here. It's very hard to make this 10 megahertz fit into this RF frequency here. But I'm wondering if we can. Because I could take this output divisor off. No, maybe I could actually probably use the divider. Anyway, maybe I'll play around with that again. Just because if you go into this integer mode here, then you don't rely on the noise of this sigma delta converter to work. You can actually do an integer conversion. You know what, I might have a play with that in a bit. This clock divide mode, I've just left how it was set by BG7TBL. Don't really care what that is. This digital lock detect, this is what I need for determining if the lock's there. These things, again, don't really need them. This is just whether you actually power the thing on or not. Count reset actually holds it in reset.
Oh, mute till lock detected. I have that on. I don't really want it to output a signal until it's locked, just in case that signal kind of goes everywhere or causes problems. I've disabled the aux output. I've verified by looking at the chip that the aux output's not connected to anything. So I've just turned it off and left the RF output enabled. No sense in having it drive, the ground plane with its signal. And then finally, this band select clock is just set to 125 kilohertz. This really is needed if you change frequency. The ADF 4350 has to kind of find what band it should operate this voltage controlled oscillator in. And you basically, if you want a fast response in frequency changes, you want this to be as high as possible. 125 kilohertz is the max. But I mean, again, we're not changing frequency, so that's fine. So what we do then is we've got our registers here. We just copy these out, and the way I've written the code now is that you just essentially write shift word and you write reg 5, 4, 3, 2, 1, and 0. So you'll see that these things here that we've got, this D40038, that's the last one, that's reg 0. Reg 1 is the one above, and so on. So this is our setup for the HP systems, and I've got above commented out, with an if false. This is the setup for those, was it an Anritsu systems. That's the original setup. So I can go back to that if I need to. And then you'll see in the Arduino code, I just have a couple of functions that help me write these words out on the serial bus. So yeah, and let's give that a try.
And it works. What great news. So what you'll notice here is this unit here is set for 930 megahertz center frequency with a 0 span, so it should be constantly looking at 930. If we do a peak search, we see a spike coming out of the system at 930. So everything works. So if I now preset this, reset these to their original state, and I put the output of the tracking generator into the spectrum analyzer, what you're going to see is the tracking generator output over the full frequency range of the system. And there you go. Nice. So what we're seeing here is it drops from there to a first peak of minus 34 dB, getting up to minus 25, minus 19, minus 16 dB, minus 14 dB, minus 11.9, and then minus 17. So minus 11 is about as high as it gets. Now that's with the level adjust thing turned all the way there, and there's some odd kind of ripples on this. I mean, I haven't got any of the shields back in place, so it might be that. Let's just try dropping the output level. Okay, with the output level all the way down, I get something a bit flatter, but okay, so I'm not happy with that output level. I think something odd's going on there. I'm going to have a quick look into the actual level control circuit and just see what's going on. This is sort of embarrassing. I found out what my problem is. So if you have a look, I started changing cables, and I noticed that the behavior of the this oscillation changed as well. So you can see here now I'm seeing a lot more oscillations here than I was previously, although I'm seeing output levels to be the same. And wouldn't you know it, it was my own fault. So I was using, let me see if I can get this to focus. I bought these adapters off AliExpress. I mean, I don't have a lot of RF equipment. This just literally arrived, but I have very little RF equipment, so I'm buying a lot of stuff off China. And yeah, these are reverse polarity SMA. So while it's got this outer, male connector, its inner side is actually female. And I was mating a reverse polarity male to a normal polarity female, so there's basically no pin between the connection, and that's what you see here. And I did also have one of the connectors that I was using, this BNC to normal SMA, female SMA, is actually bad, so there's no connection between them. So that was another source of these problems. But this actually led to kind of an interesting observation about this tracking generator unit. So what's actually happening is these two, if I just pause, I'll just save this trace. So yeah, so there we are. So if I remove this, what you're going to notice is that this, I'm connecting one of these female SMA connectors to this type N to male reverse polarity SMA connectors. And when they connect, you actually don't make a connection. Now, the signal can jump across, but it's strongly attenuated. But at the same time, what will happen is you'll get a reflection from this open end that travels back up towards the tracking generator. Now, interestingly, this tracking generator has its automatic level control right on its output. So these reflections come back, and there are additional power. If they interfere constructively, depending on the length of this cable, they might interfere constructively or destructively, depending on the frequency. And so I think what we're seeing here, the peaks, are when the reflected waves interfere destructively at the level control, the point of the level control. So the unit thinks, right, I'll bump up the output power to level it. But actually, when you're further away, these waves might not be interacting in that way. And so you actually measure at the spectrum analyzer what jumps across the gap. So the actual transmitted power goes up, but it's only because the reflection here is interfering with the level control circuit there. And vice versa, you know, so at these dips, what's happening is you're getting a reflection that peaks and interferes constructively at the automatic level control because your frequency has changed and so is your wavelength and so on. And that's where you're getting one of these troughs. So that's an interesting issue with this tracking generator. If you use it with objects that have high reflections, you're going to get oscillations in the output power because of the reflective wave. Now, you can do something about that though. So what we can do is put an attenuator in here. And the attenuator works two ways. It actually attenuates not only the transmitted signal, but also any reflected signals as well. Now I don't have a lot of RF gear, so I only have the 20 dB attenuator that I had. But we'll try inserting that and then see what happens with this reflection then. See if we still get these oscillations. Because if it's not this reflection effect, we would expect this to remain the same but just be 20 dB lower. So let's take a look at that now. Okay, so with this 20 dB attenuator in place, what I've actually done is I've installed it in this break in the cable that's internally inside the tracking generator. Sorry, let me actually show you that. So yeah, there's this extension that they seem to have inside here. So I installed my 20 dB attenuator in here, and what that will do is that will attenuate reflections coming back into this automatic level control. You'll notice, by the way, I've reinstalled the RF shield because I think everything's working, and so we're at the stage where we're going to evaluate the system. So okay, so I've installed this 20 dB attenuator here to attenuate reflections, and now what we can see at the actual output of the unit is this is the trace without the attenuate in place, seeing oscillations, and this is the trace with it in place. So 20 dB is too much. I'm losing a lot of output power here, but so I've ordered some more mini circuits attenuators, and I'll probably put like a 3 dB attenuator in there, and hopefully that will get rid of this oscillation for me. Now we're still seeing this kind of odd behavior, not a very level output, but as I said, that's because of the reflections that we're seeing, in trying to mate these two, reverse polarity and normal polarity connectors. So let's try it with a normal polarity connector. Let's give that a go. So here's the fully working tracking generator. So all I've just got is it's just a straight bit of coax between the output of this tracking generator and the input here. I still have the 20 dB attenuator in place, so I'm going to get 20 dB less output out of this than I would have without it in place, but I'm getting this kind of nice behavior when I have reflections. And if you have a look at this marker is reading out minus 8.31. So that means the output of this tracking generator turned all the way up is actually going to be closer to 12 dB, which is really quite cool. That's exactly what I want to see coming out of this tracking generator. I'm actually going to change the input attenuator to actually say that there is actually a 20 dB offset. So let's hit. So now this is actually, I've actually altered the unit to actually know that there is a 20 dB attenuator in front of its input, and it's now reading 11.69 dB. So yeah, really happy with that. That's pretty flat. You can see there's a little bit of roll off here, so if I just drag this marker over to this peak over here, at about 1.6 gigahertz, we start to see a roll off in output power. And to be honest, you know, we expect that because the mixer, the internal mixer is only rated up to 1.5 gigahertz. So it's not surprising to see a little roll off in output power there. But even so, you know, getting up to the full frequency range of this spectrum analyzer, you know, I'm reading 6 dBm here versus I'm reading 12 dBm at the peak. And I start to see a noticeable roll off while we drop below 10 dB in the somewhere around about 60 megahertz or so. So I'm pretty happy with that. That's definitely a good enough tracking generator for all my purposes. So what I'm going to do now is take a look at a couple of other things. So for example, I want to look at what actually comes out this tracking generator, how pure is its tone, and I'm also going to look at some things like the frequency accuracy of this. So just have a look at what these frequency adjust does. So if I just play around with this frequency adjust here, I see no effect on my spectrum analyzer. So I want to know exactly what that does, what the limits of that are. I should show the level adjust as well. So if I drop the level, what you'll notice is you start to see a roll off that comes in at lower and higher frequencies. And essentially once you drop this this level control all the way down to its lowest point, you basically hit a -8 dB signal. You know, -9, -10, -10 dB at 900 megahertz, and -12 at 1.5 gigahertz, and then you get the roll off again from the mixer. Now that isn't my noise floor. You can see if I turn my tracking generator off, you know, there's still quite a lot of signal coming out of this, but that just seems to be the limit of the automatic level control. Okay, so let's put that back up, get it to be roughly 10 dB, and then we'll start to take a look at things like the frequency control. So what I've done is I've attached my frequency counter here to the back of this tracking generator, and I've actually got it on internal oscillator mode, so it's actually putting out the 10 megahertz of its internal crystal out into the front of my frequency counter. Now this frequency counter is actually an ex-military one from the UK MOD, Ministry of Defence, and it has a rubidium time source inside of it, frequency reference. Now it's still in its warm-up region, that's why you're still seeing this oscillation around in the frequency. So we'll have to wait for that to kind of warm up first before the rubidium source works. But what I noticed was, if you look at this number here and you adjust the frequency at the front of the unit, what you're actually doing here, so this is the control all the way over to one side, you're actually adjusting the reference 10 megahertz. So this is the frequency control all the way to one side. So what we've got here, we've got 3 digits now. So you're looking at maybe 50 megahertz here, sorry, 50 hertz off. And if I rotate all the other way, you can see I'm about 60 hertz off here. So this front control frequency adjust knob actually seems to change the reference frequency of the internal crystal oscillator by about plus or minus 50 hertz. Now that's kind of strange. I mean, I don't know why I need to adjust the crystal frequency that much. And I've noticed something else as well. This potentiometer. So I said originally that these potentiometers were overridden by the front panel ones, but that's not true for the frequency adjust. It's true for the level adjust, but it's not true for the frequency adjust. This seems to be a coarse set, and then this front panel dial is used to set the fine difference. But I don't like the idea of having a frequency adjust on a crystal oscillator that I can knock and actually detune the system. So I actually much prefer disconnecting this. So I'm going to leave this off, and then I prefer to actually adjust this precision potentiometer down here. So it's a good potentiometer for these types of adjustments. I prefer to adjust that myself and actually tune the crystal until it was I got 10 megahertz on my rubidium counter. And then leave that at that. I mean, if I want more precision, if I want a better phase lock, then what I'm going to do is actually not use the internal crystal oscillator, but instead feed in the 10 megahertz reference from my spectrum analyzer, or maybe even distribute the 10 megahertz rubidium reference from this thing. Wow, this is really taking some time to warm up. Yeah, I might pause the video for a minute while that warms up. Okay, and sure enough, my rubidium counter has now warmed up. It's stopped wandering all over there, and I've adjusted this precision potentiometer in here until I read basically 10 megahertz on the nose. And I have to say, actually, I adjusted this potentiometer yesterday, and you know, turning on the frequency counter, it's still hitting 10 megahertz despite the 5-degree temperature change in my lab here. So I definitely think, you know, in terms of modifications for this, adding a 3 dB attenuator in here, disconnecting this frequency just pop, you're only going to ruin your frequency accuracy. Trimming this precision potentiometer on the board to give yourself a nice accurate 10 megahertz, and then, you know, not even using the internal reference if you want a proper phase lock. But I have to say, it looks pretty good. You know, there's not much drift of this. Oh, we can do a quick experiment. We can blast some cold spray into the tracking generator just to see. You know, so I've got some of this super cold spray that lets me track down thermal errors. You know, like dry joints. Let's just see what happens when I give this a dose. Okay, so we're getting a bit of variation, but I'm pretty impressed given this is not an oven-controlled oscillator, but it's actually just a, you know, what's used in here. What's used in here is actually this tiny SMD crystal just here. You know, so that did very well. It did very well. Holding up to that spray of kind of ice that just formed over the top of it. One of the things I actually did trying to debug this is I actually injected an 80 megahertz signal into the LO port of the unit, and then actually used my oscilloscope, which, you know, can work at 80 megahertz, to track the RMS voltage after each capacitor, the pi filter, the DC blocking capacitor, and through each of the stages of amplification and attenuation, because I was really trying to debug this amplitude problem that I was seeing, the low amplitude and the oscillations in it. And this is what I went to, the lengths that I went to get that done. And it's funny that in the end it was just a bad cable. Eh? So what I'm going to do is I'm going to store my notes by just sticking them to the inside of this case and then sealing them away once my 3 dB attenuator comes that I can install on the top of this unit. Okay, let's look at the spectral purity. That's what I'm going to look at next. Right, so to look at the kind of output of this, what I've decided to do, I've still got this over its full range, but what I'm going to do is lower the video bandwidth, and that essentially slows the scan rate of this unit down. And then we can just basically take a look at what happens at lower and lower scan rates. Yeah, that's better. Okay, so we're now starting at 0. There's our actual peak. Fading up here. So let's just get that marker. Where is it? Okay, so this is with the 20 dB attenuator in place. What you can see is there's one mixing product that's kind of working its way backwards while the main sweep, the actual signal of interest, is moving forwards. And there's a couple of frequencies where we get quite a lot of additional product spiking just for a moment. I wonder what that frequency is. Let's see if we can zero the span. Okay, so there we are. Now, if I start to scroll the frequency up, there should be a point. Aha, you see there. So we're hitting, what are we hitting here? We're hitting 1.6 gigahertz, and we start to see a lot of products here. Just for a moment. A lot of noise down there. I wonder why we're seeing so much noise just as we hit 1.6 gigahertz. I wonder what the offset is there. So certainly these higher frequencies, as we get towards 1.8, 1.6 to 1.8, you get a lot more products up here. Do you know what this is? This is as we get outside the range of that mixer, that first mixer. So at 1 point, let's just check that. So at 1.5 gigahertz, at 1.5 gigahertz, we're seeing a pretty clean spectrum, just two additional peaks here, but they are, what's that, 30 dB down from the main signal. And then as I get to 1.5, 1.6 gigahertz, just as I get to 1.6, you suddenly see the appearance of some more mixing products. I mean, they're all pretty low compared to the main signal, but they all appear there. So it's kind of interesting to see that as you're getting outside that rated range of that mixer, we start to see a lot more mixing products appear. But certainly while we're in, let's just change the span again. 0 span. Oh, the frequency. Certainly while we're at, this is 800 megahertz. There's a couple of spikes up here. Well, that's interesting. So that's up near 3 gigahertz. So maybe another thing that I would do. Yeah, peak 4, what is that? 2.9 gigahertz. So there might be more products at higher frequencies that I can't see because I've only got a spectrum analyzer that goes up to 3 gigahertz. I'm surprised that 3 gigahertz peak isn't attenuated by the internal filters. It might be worthwhile not only putting a 3 dB attenuator here, but just to clean up some of these higher signals, if you want to, if they matter to you, putting a low-pass filter on the output. That might actually be another good idea. All right, I am actually pretty happy with this. I think this is a top quality device considering it's available for about $100. I would definitely add this attenuator on the output. I would definitely disconnect this frequency adjust and then trim the reference. It looks like it has a pretty good crystal in there, or at least reasonably stable over the time I've used it. And apart from that, I think it's a great little tracking generator that you can now modify using an Arduino script and an AVR programmer to actually output or work with any spectrum analyzer that you want to, provided it's up to about 1.6 gigahertz. Right, thanks for watching. Catch you next time.